This experiment will show you how much heat is taken away when ether evaporates. We need a beaker, a dish, a hand pump, 2 thermometers, an electronic balance, a retort stand with a clamp, some ether and some water. The room temperature is now 20 degrees Celsius. First, we pour 40 grams of water into a dish. Then, measure its temperature with a thermometer. The temperature of the water is 20 degrees Celsius. Pour 40 grams of ether into the beaker. Measure its temperature with a thermometer. The temperature of ether is 20 degrees Celsius, which is the same as the water and the room temperature. Then, put the beaker in the dish of water. Set the balance to 0. Pump air through the ether with a hand pump continuously to speed up the evaporation of the ether. After a few minutes, when approximately 14 grams of ether has evaporated, we can see the water has turned into ice, and the temperature has dropped to 0 degrees Celsius. Can you calculate how much heat was taken for 14 grams of ether to evaporate? And among it, how much heat came from the water?
2. Specific latent heat. Latent heat is the energy change during the change of state of a substance. So, how much energy is absorbed by the beaker of ice to melt completely? Obviously, it depends on how much ice in the beaker is. In other words, a larger mass of ice absorbs a larger amount of energy to melt completely. Specific latent heat is the energy change per kilogram of substance during change of state. For example, when 1 kilogram of ice melts, it absorbs 3.34 times 10 to the power 5 joules of energy to melt completely without a change in temperature. So the specific latent heat of fusion of ice is 3.34 times 10 to the power 5 joule per kilogram. Therefore, specific latent heat L equals energy change Q divided by mass m, and thus L equals Q over m. A. Specific latent heat of fusion of ice. Experiment 3C. Measuring the specific latent heat of fusion of ice. The following experiment may determine the specific latent heat of fusion of ice. There are 2 sets of apparatus. The experimental apparatus has the heater connected, while the control apparatus has the heater unconnected. The ice on the right, the experimental apparatus, is melted by both the heater and the surroundings. The ice on the left, the control apparatus, also melts, but melted by the surrounding temperature only. So, the control apparatus may find out how much ice is melted by the surroundings during the experiment. There are a lot of precautions in this experiment, such as using crushed small ice pieces, ensuring the drip rates are the same at the beginning and end of the experiment, and using a small wire gauze to avoid ice falling directly into the beaker below. Let's now take a look of the experiment.
Pack the crushed ice so that the drip rates from the 2 funnels are steady and about the same. Take the initial geometer reading. Put beakers underneath the funnels and switch on the heater. After about 5 minutes, switch off the heater. When the drip rates become steady and about the same, remove the beakers and measure their masses. Take the final geometer reading. Record the results and calculate the specific latent heat of fusion of ice.
On the other hand, you may also calculate the specific latent heat of fusion of ice from the final temperature when mixing ice with water. Example 2. Finding the specific latent heat of fusion of ice. Using a similar experiment, the following data may let you calculate the experimental value of the specific latent heat of fusion of ice. You can see the percentage error is still large, as many sources of error are difficult to avoid. And yet, some errors may lead to a smaller or a larger calculated specific latent heat, while some errors will lead to a larger one only. Example 3. Heating ice. And now you may calculate the energy change when ice is melted and when water is later heated to higher temperature. Try checkpoint 2 below.